A very good morning to all. I request every participant to stay tuned the meeting till the end, and please put your microphone and camera off. And please, Ali Haidar, take your time now.
Okay, hello everybody. So I start. So I'll talk about concentration phenomena for Liouville type equations. Okay, so here is the plan of the talk. So omega is a bounded domain in R2. So it could be just simply unit ball or any bounded set, or even something unbounded is okay. Also, sometimes I would consider omega equal to just the R2. And we consider this PDE minus Laplacian u equals to exponential 2u in omega. And here we are assuming that the integral of the right hand side, exponential 2u, is finite. So first I will mention about the Liouville's theorem. So and it gives some sort of a representation of the solution u using complex analysis. Then I will talk about geometric interpretation of this equation PDE in terms of Gaussian curvature equation, and then next would be to do analysis from PD point of view, and at the end I will also mention some results when this PDE is replaced by a higher order one, and the domain dimension of the space is instead of 2 it would be like 4, 6 or anything. Okay, so the Liouville's theorem. So let me just recall the notation because I will use it again and again. So minus Laplacian, so is just second order derivatives, partial derivatives in both directions. And when the domain dimension is Rn, space is Rn, then we have to take all the partial derivatives of second order. And here this minus sign should be always minus sign. So Liouville's theorem states that any solution to this PDE in R2 is given by log of 2 f mod f prime z by 1 plus mod f z squared. Here z equals to x1 plus ix2 and x equal to x1 x2 in R2. This is the standard identification between the complex plane and the plane R2. And the function f is just a locally injective meromorphic function on the complex plane. So in particular it could be also a holomorphic, but in general it is locally injective. And this theorem actually is a bit more general in the sense that we don't need the space to be whole R2. In fact, this representation is also true if we replace R2 by any simply connected domain. And this proof is based on complex ODE theory. Okay, so what is the advantage of this representation? So if you just know on local injective meromorphic function, then you get an explicit solution. So for example, fz equals to z, the simplest one, that gives ux equals to log 2 by 1 plus mod x squared. So simply plug in here and you get this representation, explicit solution. And not only this function, instead if you put a 1 by z, f equals to, you get the same function u, or z plus 1 by z minus 1, you get the same one. And more generally, just use a Mobius transformation for these functions, you always get the same function. And this fact is due to, because of this PDE is conformally invariant. Okay, so this is one type of solution. Next one is fz equals to exponential z. In this case, you get ux equal to log of cosine hyperbolic x1. So if you notice, okay, so this exponential z is a local injective, not global injective, but this global injective, this one, for instance, or this one. And first one is radially symmetric, whereas the second one depends in just in one variable x1. So next, we want to characterize this first solution. This is good and in some sense, and it also appears in geometric analysis. So basically, so that's why I would give a characterization of this solution in the next slide. So the corollary of the previous Liouville theorem is the following. We take the same equation on the whole space, and if, okay, so in this slide, we did not assume that the integral of the right-hand side is finite, okay? But if we assume that this is the additional condition, the integral is finite, then the solution should be of this type: log 2 lambda by 1 plus lambda square mod x minus x naught squared. And x naught is a point in R2, any point, and lambda is positive. So here, because this PD is invariant under translation, so that this is why we have x naught. And at the same time, it is invariant under some dilation, and that is the lambda parameter. Before going to the proof of this corollary, let me just recall some basic properties of meromorphic functions for the students. So if f is a meromorphic function on the plane, and it has no essential singularity at infinity, then f is a rational function. That is, it is given by a ratio of two polynomials. Next is locally injective. Then it can have only simple poles, and at the regular points, the derivative should be non-zero, because if the derivative is 0, then the function behaves like z squared or z cubed or like that at that point, and that would violate the local injectivity condition. And these two properties will be used in next slides. Okay, so because of this additional hypothesis that x integral is finite, and because of from using the representation we get this is finite. So in roughly speaking, the integral is finite means this function has to be small at infinity. Of course, is not in a point, in some very rough sense. And that means the function f cannot have essential singularity at infinity. So in other words, then f has to be a rational function. So that this limit z goes to infinity f of z mod f z, I need to put here, it is either plus infinity or it has a finite limit, some c0 belongs to c. Then again, after some transformation, we can make the second case to the first case. We can assume that limit is infinity. And since we already know f is a rational function, we can write it as a ratio of two functions p and p by q. P and q, they are two polynomials. And we can also assume that they do not have any common factors. So basically, the zeros of two polynomials are different. And so derivative is q p prime minus p q prime by q squared. So as I mentioned before, that at the regular points, f prime cannot vanish. And so that means that q p prime minus p q prime has to be a okay, so both are polynomials. So this difference is also numerator is a polynomial, and it cannot vanish. So it has to be a constant, basically non-zero constant. Because if it is a polynomial of some degree, then it has a 0. So that cannot happen. And q has to be identically constant. These are the only choice. Then necessarily you get p is of this type alpha z plus beta with alpha non-zero. And here this beta is sort of a translation, and alpha is kind of the dilation. And since p is of this type, then that is f is again of this type, because q is identically constant. Then you put it back to this representation here, then you exactly will get this solution of this type. Okay, next let's talk about the geometric interpretation. So Mg is a smooth surface in R3. So then a natural question in conformal geometry is that, can you find a conformal metric Gu? So that means G is given, and you want to find a metric Gu which is a scalar multiple of G, and this multiplicative factor would depend on the point of on M at this point. So here U is like a smooth or C2 or some good function on the manifold M, and such that this metric GU has constant Gaussian curvature. So in terms of PDE, this question is equivalent to existence of solution to this PDE on the surface M. So here Kg is the Gaussian curvature of the given metric G, and K is the constant that what I want, the constant Gaussian curvature, this constant, so K is just a constant, and minus Laplacian G is the Laplace Beltrami operator on the manifold. So in the particular case, like in the flat case, like plane with the d square standard metric, we have the flat means the Gaussian curvature is 0. So this equation is just minus Laplacian u equals to k exponential 2u in R2. And in my previous slides, I put just k equals to identically 1. Okay, so this is my equation, and so if the manifold is smooth, yeah.
Alida, 1 minute, please. Alida.
Yeah.
Please everyone pin the PPT. If you are not seeing this, please pin the PPT. It is already open. Thank you. Continue.
Okay, thank you. Okay, so now what about the regularity? So let's say U is M is a compact closed, so that is compact without boundary sort of surface like a sphere, torus. So in that case, U is a smooth function, let's say, then integral of the right hand side is always finite. So this is my PDE on the manifold, and integral is finite. So geometric meaning is that K, as I already mentioned, K is the Gaussian curvature of this conformal metric GU, and this integral exponential 2u times dvg, this is actually volume of this conformal metric GU, and the total integral of the right hand side, if I also put K here, then this represents the total Gaussian curvature of the metric GU, because dvgu is this part. And so I am integrating the Gaussian curvature with respect to the metric, so that's why I get total Gaussian curvature. Okay, so now relation between R2 and S2. So we know that on the sphere S2, and we fix the north pole N, then you pick any other point capital Z on the sphere, then join the north pole and that point Z with a straight line and extend it so that it will hit the plane R2. This slide is not visible?
No, not visible.
Yes, yes, visible.
Okay.
I request Ali sir, please
No.
reopen this. Please stop the PPT and reopen this.
Can you see it now?
Yes, is it visible?
And this one?
It is visible. Please.
Okay.
Continue.
Okay, so this is the stereographic projection. So in simple form, if x1, x2, x3, this is a point on S2, so that is a point in R3 actually. Then tau is the projection is given by x1, x2 by 1 minus x3. So in particular, where if I go approach North Pole, so that means x3 would be close to 1, then this point would go to infinity. Okay, so as I was mentioning about the Gaussian curvature equation, so on the sphere, for S2 unit sphere, the Gaussian curvature is identically 1, and so this is, and for the round metric S2, we have, this is the standard equation. And if W is a solution to this equation, and if I define U in this way, so on R2, so I am taking a composition with this stratigraphic projection and adding a function log 2 by 1 plus mod x square, then U would be a solution to the PDE in R2. So in this way, given a solution on S2, we could obtain a solution on R2. And because of this geometric way of getting it, these sort of solutions are known by spherical solution. Now, if you look at here, W equals to 0 is a solution because this part would be 0, and here 1, 1. So this part is 0. We get just log 2 by 1 plus mod x square, that one solution. This is what I already mentioned. Okay, now we move to PD techniques and PD approach basically. So what I mentioned before, using the Liouville's theorem, that all the solutions to this PD under the finiteness of this integral is of the type log 2 by 1 plus mod x square after scaling. It can be also proved using some PD method. So, and since these solutions are explicit, you can also compute this integral, and you will get that value of lambda is exactly 4 pi. And this value is quite important, and it will appear later many times. And if you do a translation or dilation, all of those solutions would also satisfy lambda equals to 4 pi. And okay, also let me just tell you why this is 4 pi. So basically, I am obtaining the solution in this way, and think of this way, that if that integral of this right hand side exponential to u is like on R2 is like exponential to W1 S2. Now if you integrate here, then you get integral of S2, that is 4 pi, and that is the integral, because this part, integral of this part would be 0. Okay, so now to do some analysis using PD methods, it is important to know what is the fundamental solution. So for Laplacian, log of 1 by mod x is a fundamental solution, that is minus Laplacian log 1 by mod x is equals to 2 pi times delta naught. So this delta naught is the Dirac measure at the origin. What it means that if you take any function phi which is smooth, or here you can just take C2, and which has compact support, then this is at least a bounded continuous function which has a compact support, then you can integrate it, and you will get exactly minus 2 pi times phi of 0. Here, if you look at here, log is a smooth function outside origin, so if you compute the Laplacian, you would get identically 0. So only the problem is you cannot take the derivative at the origin. There was a problem. And here, so if you do integration by parts, so if you put the Laplacian here, so formally this part would give us 0 outside the origin, but at the origin there will be singularity of order 1 by mod x square, and so you have to do it in a careful way. Then you would get exactly minus 2 pi times phi 0. The advantage of this thing, that is the use of fundamental solution, is that if you have a solution on the whole space, you can write using a convention. So basically, you can write u in this integral form. So 1 by 2 pi, because I need to divide 2 pi, because here I had a 2 pi, so to get p0. Log mod I mod x minus y exponential to ey dy, and there will be some constant, doesn't matter. So why do I need to put mod y here? So we only know that exponential to u, this part is integrable. So if I don't put mod y, I just put here y, then for x fixed, this whole part thing will be like log mod y times exponential to ui, and we don't know if that integral is finite or not. So this is why, to make this integral finite at infinity, we need to put a mod y. Now once we have this representation, we can get a nice asymptotic behavior at infinity, and that is good enough to start the moving plane techniques, and that would imply that the solution is radially symmetric about some point. Now once we show that it is radially symmetric, then the PD Laplacian, that is just an ODE, and then solving the ODE, you will get this is the solution up to a scaling. Okay, so next I want to talk about this equation but on a bounded domain, and instead of just one solution, we'll take a sequence of solutions, and we can study the compactness properties for such solutions. Now before I put just one here, but now you can think of qk equal to just one, or some functions close to one, and integral exponential to uk uniformly bounded, and omega is again just a bounded set, and I am not mentioning anything about the regularity of the domain omega. So question is, what can we say about this sequence? Does it converge? Does it in some point goes to infinity, some points goes to minus infinity? What happens? So this theorem is due to Bayes and Merle, and one part, and the another part is due to Ley and Siegfried. So up to a subsequence, we can have a compactness, that is uk would converge to some u infinity in c1 log omega. So here this convergence I am saying it's locally uniformly, because we did not impose any boundary condition, so we don't know what happens at the boundary or close to the boundary. And if it is not compact, then there is another possibility. So there is a finite set S star. So how it is defined? Now we choose only those points x in omega on the domain, such that on a small ball, integral of qk exponential to uk, if I take lim k goes to infinity, then it is at least 2 pi. So first I take k goes to infinity, and then I take r goes to 0. So and a small ball, there is the integral of 2 pi. Now since the total integral of the right hand side is uniformly bounded, and at each point there is at least 2 pi amount of integral, so that means this set S star is at most finite. So in the second possibility, uk would go to minus infinity in omega minus these finitely many points. Again, this convergence, this is locally uniformly. And what happens to the point around the points of this set? So you fix a point xj on x star, and then for every epsilon positive small, the integral of the right hand side q exponential to uk in a small ball would converge to 4 pi or 8 pi, 12 pi, so on, like an integer multiple of 4 pi. So next I will explain why do we for a blow up. So here the integral of the right hand side should be at least 2 pi, and then next I will explain that why the integral is goes to 4 pi or multiple of 4 pi. So the picture looks like this. So there are at this point the uk would go to in plus infinity, this point goes to plus infinity, this point goes to plus infinity, and around each point the integral is like a 4 pi. Outside these points, uk goes to minus infinity, and what could happen is that like this peak they collapse at one point. So since each peak contributes a amount of 4 pi amount of integral, then you get, if they collapse at one point, you get 4 pi like 8 pi, and that is why you will get multiple of 4 pi. Now, why do we need to have at least 2 pi amount of concentration for a block? So here is the lemma. It says that if the integral is lim sup of the integral is less than 2 pi, so here it's strictly less than, then in a smaller ball, so the integral is small in a BR, so in BR by 2, or you can actually take any smaller domain, the supremum is uniformly bounded. To prove it, we split UK into parts, WK plus HK, and here WK is given by this formula. So again, I am using some integral representation using the fundamental solution. So that means UK and WK, they satisfy same equation. So HK should be harmonic, that is Laplacian HK 0. Now, due to this hypothesis, it is strictly less than 2 pi. So that means integral is less than 2 pi. Now I put this 2 pi quantity here, then integral would be less than 1. Then I can multiply by little p bigger than 1 to make it 1, and use Jensen's inequality to show that exponential 2p wk dx is less equal to c for some p bigger than 1. Okay. And about the function hk, it is harmonic, so we can use mean value theorem to conclude that hk less equals to integral on a br by 2 hk plus y dy, and hk plus, again because of this splitting, is less equals to uk plus wk. And again here, if we integrate wk using Fubini's theorem, we get this whole thing is uniformly bounded. And but now we are in a smaller domain. So this last estimate tells us that uk less equals to wk plus a constant in a smaller domain, and the function wk has some higher order integrability. So wk is better than uk, because for uk we knew just exponential 2 uk is integrable, uniformly bounded integral, but now I can make it a little bit better because p is bigger than 1. So in other words, since qk is like 1, I can ignore it. Exponential 2 uk, it is in uniformly bounded some LP space. So then here I can use a Holder inequality to conclude that wk is uniformly bounded on a smaller domain. So wk would be uniformly bounded, and hk has upper bound, so that would give an upper bound on uk. Okay, so this explains why we need at least 2 pi amount of concentration. Next is, why do we have 4 pi? Okay, so simply assume that uk of xk goes to infinity, and this is the maximum. So that is the height of the peak. Then we do a scaling in this way, and this is the standard one for Liouville equation. Eta k equals to uk xk plus rkx minus uk of xk. So since I am subtracting the maximum value, this is less equals to 0, and at the eta k at 0 is our integral is 0, and rk, it goes to 0, but in this nice way is given by this formula. Then eta k satisfies a nice integral equation PDE. So basically it is locally order of this notation is like locally uniformly bounded independent of k, and also at the same time the integral exponential to eta k is less equal to c, and r is any r large fixed, and qk tilde is just the scaling of qk because of this translation and scaling. Then one can use Harnack inequality to conclude that after subsequence eta k would converge to eta, because this is a uniformly bounded part, and eta would satisfy this PDE. So think of qk tilde is identically 1, it converges. So this is Laplacian eta, right hand side exponential to eta in R2, and integral is uniformly bounded here. That gives the integral on whole space R2 is finite. And I have already mentioned that in the equation on R2 and integral finite means the integral is exactly 4 pi. And this is how we get 4 pi. For the total integral around this peak is 4 pi. Okay, now next we move to a higher order case, namely the fourth order case. So before I was considering Laplacian, so that was the second order derivative on a domain in R2 in dimension 2. Now we are in dimension 4, R4. So, and order of the operator is also 4 because I am taking Laplacian twice composition. So it's a fourth order operator, and also integral, assuming that integral is finite. So as before, now we do not have any more the techniques using complex analysis. So only we have PD approach basically for all the analysis. The 16 pi squared quantity plays the same role as 4 pi before. Okay, so now the solution U, it has this sort of asymptotic expansion at infinity. So it is like a log x, and there is a polynomial, it is of degree 2. There is a minus sign and ai get equal to 0. So basically p less equals to, it has an upper bound. So why do we get a polynomial? Because if you take a fourth order derivative on p, then this should be 0. So, and here the operator is a fourth order. So that means this sort of polynomials are in the kernel. So then why is not third order polynomials are also in the kernel, but they cannot be here because this first part is like a log x, and if there is a third order polynomial, they need to be sign changing, of course, and in some direction it would go to infinity too fast. So that would dominate because log is a smaller than the polynomial, and that would violate the finiteness of this integral condition. And exactly because of the same reason, this ai has to be greater equals to 0. And what is more interesting is that before we had lambda, the integral was just 4 pi, but now this integral could be anything between 0 to 16 pi squared, and for every lambda between in this range there is a solution, and the solutions for which this polynomial part is non-trivial, we call them non-spherical, and if it is trivial, it is identical constant, that is solution is like a log x, it is, we call it a spherical. Okay, so now in the from dimension 4 to like in general case, so you can think of in Rn for any n, so if n is odd, then here there will be fractional Laplacian, and if n is even, then this is just a polylaplacian, and always the integral is finite. So let me just mention you briefly the results without giving any details. So what happens in dimension 2 is exactly the same thing in dimension 1. Same. What happens in 4 is like the 3, and all the other dimensions bigger equals to 5 are the same. So dimension 1 and 2 on only spherical solution, and value of lambda was like 4 pi in and for dimension 2, or is like 2 pi or pi, something like that. So it's just one fixed quantity. 3 and 4 lambda is in between 0 to some lambda in star, but in dimension 5 and higher, it could be anything in between 0 to infinity. And here are some of the references for these results. And these fourth order equation or higher order equations are also geometric. So this function q is the q curvature of this conformal matrix G, and this q curvature is a higher order analog of the Gaussian curvature. The integral exponential 4u dx is the volume of the metric G. Okay, I should have used the notation GU instead of G here. And q exponential 4u dx is the total q curvature of the metric, this conformal metric. Now, what about the compactness for a sequence of solutions as before? So now we are considering a sequence of solutions on a bounded domain or unbounded, doesn't matter. But again, integral is uniformly bounded and qk is like 1. So up to a subsequence, you can have a compactness, or there is a blow up. But now the blow up part is completely different than the previous one. So now what we can say is that there are some large numbers beta k goes to infinity, and if we divide it uk by beta k, then it converges to a function phi. This is a biharmonic function, Laplacian 2 phi equal to 0. It is non-positive and non-trivial. And about this convergence, it holds in omega minus set S, and this set S has two parts. One is a finite part, is a union of two parts, S tilde and SP. S tilde part is a finite, like as before, but there is an additional one, this one. The zero set of this function phi. And it can have dimension 3 actually. So this blob set could be quite large. And the picture is like this. So there are finitely many peaks, like this tilde, and there is a zero set where also the blob occurs. Now, is there a way to recover the blob analysis of dimension 2 in higher dimension case? So for that, you need to assume that integral of Laplacian UK is uniformly bounded. So under this extra assumption, the blob set would be finite, and the picture is exactly like dimension 2. And around these peaks, the total integral of the right hand side and smaller ball, it would be a multiple of 16 pi squared. So as before, again, these peaks can collapse at each point, one point, and then you get a multiple of 16 pi squared. So I was interested in doing this, proving this sort of result, but without this additional hypothesis. And actually, interestingly, we can say something like that. So around each point xj, S tilde. So here S tilde set, so S minus SP. So if I stay outside the zero set, then we can say that this integral actually converges to multiple of 16 pi square. But I do not need any assumption like this one. And what is more interestingly, these two random quantities like beta k and the maximum of uk, that the height of the peak, they are related by this relation. This is quite interesting because the beta k quantity appears completely in a different way, but they are not just arbitrary large numbers. It is related with the height of the peak. And some different kind of blowing up solutions, more existence of blowing up solution. So in a model case, like radial symmetric case in dimension 6, and simply take qk equal to 1, or radial symmetric, and now the equation would be I'm in dimension 6, so Laplacian 3, and I take simply the domain to be B2, and the integral is uniformly bounded. So just simply doing a scaling, so you can construct solution which blows up just at one point, and outside it goes to minus infinity. This is trivial, first case. Second case is the blow up occurs on the unit sphere S5 mod x equal to 1 set. This is a bit complicated, but not that difficult to prove. So interesting question is, can you glue these two things together? So what we are asking is it possible to have a blow up on the sphere and like this one, and at the same time blow up at the origin like this one? And the answer is yes, we could do it. And in this case, because of the previous theorem, the integral of this peak would be exactly 16 quantity like 16 pi square and like a spherical one. Okay, maybe now I should stop here, and there are 5 minutes, so you can ask many questions. Thank you for your attention.
Everyone, let's thank Ali for his interesting talk. Maybe anyone have some questions? The application, the questions are raised in the chat. Where is application of this topic in modern times?
Okay, so basically these are application is in geometry basically. To prove existence of manifold with given prescribed Gaussian curvature or Q curvature and so on.
So please also ask a question. I see that someone else have.
Yes, but no one mentioned. Okay, there is what is the application of this topic modern times. Okay, it applies to geometry. And so any other question? Okay, citing some okay, so okay. Okay, so basically the question is this one. So you just have a smooth surface, and this is a uniformization theorem. Like there is another one, you may have no Yamambe problem. So where you ask the existence of a surface with constant scalar curvature or existence of a surface with constant Gaussian curvature. So in those cases, you need to understand the existence of solution to this equation. And then instead of Gaussian curvature, you want to know the existence of a manifold of even dimension, or nowadays also odd dimension, with the prescribed Q curvature. Then again you want to study this sort of equation higher order case. And in fact, this problem is still open, and which is known by Nirenberg problem on S2. So you take a m equals to round sphere S2 and fix a function k, given function k. Can you find a solution to this equation? And this problem is still open, and it was raised around 80s or 80s or something like that.
So any other questions? So if there are no questions, let's thank the speaker for his bright talk and wonderful presentation. Thank you, Ali.
Okay, thank you everyone. Thank you very much for your attention. Okay, everybody, have a nice day, and I will quit now and go to bed. Bye bye, everybody.
Thank you, our honorable speaker, Dr. Ali Haidar, for his nice lecture, and also thanks to our honorable chairperson for giving us his valuable time from his busy schedule, and also thanks to our participant for their cooperation. Now I am inviting our next honorable speaker, Dr. Nikita Frolov, senior researcher, Innopolis University, Russia, to deliver his valuable lecture. And in this session, on behalf of webinar organizing committee, I would like to request Dr. Kollan Haldar, Sidhu Kanu Birsa University, for chair this session. Dear participant, please enjoy this session with our speaker. Now I handed over the chair to our chairperson.
Thank you, sir. Very good morning to all. Am I audible? Hello?
Yes, audible.
Yeah.
Yes,
good
audible.
See my screen?
Yeah. Very good morning to all. At first, I would like to
No.
express my sincere gratitude
Yes, sir. Yes, sir.
to respected delegates, dignitaries, and audience. I am feeling very privileged to have the opportunity to take the chair for this talk of renowned researcher, Dr. Nikita Frolov. For this, I must convey my heartiest thanks to the organizing committee, especially the convener of the webinar, Professor Pintu Mondal, and also joint conveners, Dr. S.K. Amanatullah and Dr. Jinarul Haq Sheikh. I also impart my profound gratitude to the chief patron of the webinar, as well as principal of Raghunathpur College, Dr. Falguni Mukherjee, and all respected invited speakers to enrich and make luminescence this web event with their cognitive repositories. Before start of the lecture, I would like to say a few words about Dr. Nikita Frolov. He is from Angels in Russia. After completing higher study on radio physics and electronics in Saratov State University, Russia, he pursued as researcher in that university. He also acted as a researcher in Potsdam Institute of Climate Impact Research in Germany. At present, he is working on neuroscience and cognitive technology lab in Innopolis University, Russia, as a senior research scientist. His ongoing research and scientific interest lies in the area of the complex networks theory and biological multivariate data analysis based on the machine learning and network methods. He has 53 publications in reputed international and national journals till now. Today, he is going to deliver his valuable talk on frequency modulated chimera-like behavior in a heterogeneous Chromomoto model. I again feel honored to chair with the talk of such vast researchers. Now I request Dr. Frolov to enrich us with his innovative and informative speech. Please, sir.
Yeah, thank you for your warm introduction. One remark that I have slightly changed the topic. I have extended my talk, which cover a larger area of our research, which we carry in our lab. So is it okay? Everyone see my presentation?
Yeah, it's okay.
Yeah. Actual title of my talk will be devoted to chimera-like behavior in realistic network models, multiplex, neural, and heterogeneous ensembles. These studies are carried out with our colleagues from India, particularly Professor Dibakar Ghosh from Indian Statistical Institute and his students, his former student Bidesh Bera, which is now a postdoc researcher at Ben Gurion University, Israel, and his PhD students, Mr. Sarbendra Rakshit and Mr. Sumen Machi. So also we carried this research with Professor Simal Dana, Professor Jürgen Kurz from Humboldt University of Berlin and Potsdam Institute for Climate Impact Research, and the members of our lab, our supervisor, Professor Alexander Hramov, and our senior researchers, Dr. Vladimir Maximenko and Vladimir Makarov. So, outline of my presentation. First, I would like to talk about what is a chimera behavior in complex networks, and then I will discuss our recent advances in multiplex networks, networks of bistable biological neurons, and heterogeneous networks which compose altogether the models of realistic networks. Initially, chimera state was discovered by Chromomoto and Badaktoh in their pioneer work. They discovered during their numerical simulations that symmetrical ensemble of non-locally coupled nonlinear equations, particularly Ginzburg-Landau equations, could split into two subpopulations which exhibit different dynamical properties. So one population demonstrates coherence and the other demonstrates incoherence. This is rather inobvious type of behavior which consists in symmetry breaking and attracts a lot of interest due to its applications in various fields of science and technology. Later in 2004, Abrams and Strogatz proved this effect using analytical approach and discovered all the bifurcations lying behind this this phenomena. This work in physical review letters gave rise to a large area of research which now covers a lot of topics. Current state of research in this field is given in the extensive review by Panaggio and Abrams, and covers wide topics related to the chimera states in coupled Chromomoto equations. So in this slide you can see a variety of different patterns formed by chimera state. Figure A shows the clustering of two coupled subpopulations. One of them demonstrates coherent state and one is desynchronized. Figure B represents reproduction of original Chromomoto and Badaktoh results in a single population. Figure C, D, E, and F demonstrate various patterns of chimera in two-dimensional lattices of nonlinear elements. What is known by this time, a lot of researchers provided bifurcation analysis of chimera state. They studied all the bifurcations lying behind this phenomena. The stability of chimera state was also explored. Chimera in various topologies, and the possible applications uncovered by this time are unihemispheric sleep of various animals like dolphins. It means that while they are sleeping, one half of the brain, one hemisphere of the brain demonstrates synchronized behavior, well-pronounced rhythm, while the other remain unsynchronized and demonstrates noisy behavior. The cardiac system, in this slide you can see the spiral waves achieved in the simulations of the heart muscles. Power grids and social systems also exhibit such clustering phenomena. But what we are interested in moving towards some realistic models which could give good description of the real world processes. One of such networks, one of such concepts of networks is a multiplex network. which represent a multi-layer network where each node is connected to its replica on the other layer with the one-to-one coupling. This could be a quite nice model for social networks, where each network represents each aspect of social life or social network of one human. In different layers, he can be interconnected with the different people, while he can be interconnected with the other people on the other layer. Also, it's a good model for air transportation networks and neuronal processes, where each layer represents different brain rhythms. First, in our work in 2016, we have considered the chimera behavior in two-layer multiplex network. It is represented on the slide. The governing equation is a modified Chromomoto equation. The multiplex coupling, which is multiplied by lambda2 divided by 2. System parameters are lambda 1 is the intralayer coupling, which stands behind the coupling within the layer. Lambda 2 is the interlayer coupling, is the coupling strength between the layers. R is a coupling radius governing the non-local coupling. N is the number of layer nodes. M is the number of layers, which is fixed to 2 in this model. And alpha L is interlayer coupling delay within each layer. Also, the snapshots of layer dynamics are presented here. We can introduce the parameters so that each layer could demonstrate the chimera pattern. We characterize the coherence of each layer with the strength of incoherence, which is described on this slide. Strength of incoherence equals to 0 means that the layer is coherent. Strength of incoherence equals to unity means that the layer is incoherent, and strength of incoherence between 0 and unity means that there is a chimera state in the layer. So we can see that increasing the interlayer coupling, the difference between the states of the networks vanishes, and both of them demonstrate the same type of behavior. If we couple layers with different types of behavior, we can see that most of them are synchronized into synchronous chimera pattern. This slide represents two situations where one of the layers is chimera and the other is either coherent in the upper row and incoherent in the lower row. What happens if we increase the interlayer coupling strengths? This will mean that these layers will undergo the transition to synchrony, which finally gives rise to the multi-layer chimera. Which means that two layers both represent the synchronous chimera pattern. The extensive numerical analysis of this behavior on two-parameter plane, where one parameter is a phase lag on the one layer and the second parameter is a phase lag on the other layer, represents the situation where the increase of the coupling strengths leads to the transformation of this of the behavior on two-parameter plane. The chimera pattern lies on the diagonal area 2, and the increase of the coupling strengths leads to the transformation of this two-parameter plane. We have proved this phenomena, this multi-layer phenomena, using analytical solution in the framework of Ott-Antonsen ansatz, which gives the continuous limit of the network behavior. To do this analytical treatment, we consider the PDFs of phase dynamics in space-time domain using the continuity equations. Then we rewrite the order parameter, which characterizes the coherence of each layer of the network, and then we are looking for the solution in the form of Antonsen ansatz, given by the first equation in this slide. Substituting this solution into continuity equations, we finally achieve the governing equation for the analytical model. Unfortunately, the final equation is not analytically solved, but it could be integrated numerically. The results of the numerical integration the fixed parameters are presented here with the weak coupling strengths. We see that both layers evolve simultaneously interacting, and both of them demonstrate antiphase chimera behavior while their interaction. And this behavior is stable and does not depend on the number of the elements, since we go to the infinite limit of the number of the elements using the continuity equation. Next, we move to a larger network. We consider a 3-layer network, and we ask ourselves the question if we can give a rise to a chimera on the macroscopic level, which means that if we can excite such type of behavior when one of the layers demonstrates one type of spatiotemporal behavior and the other two demonstrate the other. For instance, we considered such network where each layer can exhibit either synchronous behavior, chimera, or desynchronized type of behavior. To characterize the coherence of each layer and to characterize the chimera behavior, we introduced the coherence measure, which is based on the calculation of the phase recurrence matrix given on the slide. And this parameter, this coherence measure, reflects the number of the network nodes lying in the coherence domain. So in the exemplary figure shown in this slide, we see that measure of coherence equals to 0.22, which is the portion of the coherent cluster with this, which is exactly 22 elements in this case. Introducing a weak coupling between the layers, we achieve the situation where one of the layers breaks the symmetry and goes to another type of dynamics. This situation is represented in figures A, B, and C. We can see that while in figure A, while two elements are synchronized, the other demonstrate pronounced chimera pattern. In figure B, we can see that while two layers represents chimera state, one of them represents synchronized behavior. And in figure C, two layers are desynchronized, and the third one is a chimera pattern. On the contrary, there are three areas where the dynamics of each layers represent the same type of behavior. 3 synchronized, 3 chimera, and 3 desynchronized. Providing an extensive numerical analysis of this type of behavior, we have considered 2-parameter planes of the network dynamics at different values of coupling strengths between the layers. Figure A represents the absence of coupling. Figure B represents the weak coupling, C is intermediate coupling, and D is strong coupling between the layers. So from figure B, one can see that slight increase of the interlayer coupling results in the overlapping between the regions. Completely desynchronized behavior intersects the area of completely chimera behavior, and close to the boundary between the transition, we can see the macroscopic chimera behavior when one of the layers switches to another type of behavior with respect to the other ones. The same situation is observed at the boundary between synchronized chimera transitions. So also there is observed a macroscopic chimera pattern, which we are looking for. Further increase of interlayer coupling leads to wider overlapping of the synchronized area with the chimera area, and the emergence of interlayer coherence, where all the layers are synchronized in the phase and the frequency. Finally, strong coupling leads to the complete overlapping of desynchronized area and chimera pattern, and the abrupt transition from SSS pattern to DDD pattern. We conclude, based on this extensive numerical analysis, that such macroscopic chimera behavior emerges due to the coexistence of different solutions on each layer close to the boundary between the single layer transitions. And the areas are widening with the increase of the coupling strength. We proved our results also with the analytical approach, which was the same as in the case of two-layer network. Here we constructed the network dynamics in the points A and B in the case of weak coupling, and we achieved that there is a stable analytical solution governing the effect that we address, namely the macroscopic chimera-like behavior. In figure A, one can see that one layer goes to chimera and two others are synchronized in antiphase, while in figure B, at the other boundary, we can see two desynchronized layers and one demonstrating chimera behavior. We have also checked that with this approach, that this phenomena does not depend on the number of elements within each layer, and is quite stable after a large number of cycles of numerical integrations. We have also considered the network of biological Hodgkin-Huxley neurons and addressed the issue of formation of chimera state in this network. The governing Hodgkin-Huxley equations describing the membrane potential dynamics of single neuron are presented on this slide with the set of parameters. Here, here V is the membrane potential, M, N, and H are ratio of gating of ion channels, and alpha and beta represent, one moment, they represent rate functions given in the following form for each of the gating ion channels. As I said before, the set of parameters for this system are given on the slide as well. Typically, the dynamics of biological Hodgkin-Huxley neuron is controlled by the parameter IE, which is external bias current, which controls the excitability of the neuron. So at low bias currents, Hodgkin-Huxley neuron is silent, so its behavior is characterized by a fixed point in the phase space, and the increasing of these bias currents leads to the Hopf bifurcation to the limit cycle. However, with this set of parameters, this transition goes through the bistability region. So the Hodgkin-Huxley neuron demonstrated by stable behavior between the fixed point in the quite narrow window between the fixed point and the limit cycle. So both of these solutions, limit cycle and the fixed point, are simultaneously coexist. It's worth to note that limit cycle is the unstable solution and the fixed point is a stable solution. Also, the base instability of the fixed point is presented here. With increase of the current, it loses the volume in the phase space. This attractor loses the volume in the fixed space and completely vanishes after the complete transition to the limit cycle. Interestingly, that the behavior of single bistable Hodgkin-Huxley neuron could be switched by the external pulse applied to this neuron. It is it could be shifted from fixed point in the bistable regime by the small current pulse, which is given by the figure A, B, and C. On the contrary, when the neuron is already on the limit cycle, it couldn't be such obviously switched to the fixed point, since there are three parameters of the pulse: amplitude of pulse, duration of pulse, and the phase of pulse, which control this switching. If the pulse is given in proper phase, the orbit of the limit cycle is not going near to this fixed point attractor, and after the pulse, the neuron goes again to this limit cycle. So it's not switched to the fixed point. However, if the pulse is given in the proper phase, the limit cycle trajectory is transformed in a way that the point in the phase space is attracted by the fixed point, and after the pulse, the trajectory converges to the fixed point and locked in this attractor. This interesting phenomena is the core mechanism of the emergence of chimera state or chimera-like behavior, which we observed in our work. Under the interaction and the increasing of this current bias, we observed the unexpected situation that increasing of this current leads to emergence of silent subpopulations of the neurons, when originally all of them were spiking. So increase of the coupling strength within the layer and the increase of the current bias leads to the formation of the silent cluster instead of synchronization between the neurons. This figure represents the dynamics of the Hodgkin-Huxley network on the two-parameter plane. External current bias versus the coupling strength between the neurons for three different types of topology. Figure A demonstrates scale-free topology of the network. Fig B demonstrated the scale-free topology, and C is completely random topology. We can see that small world and random topology demonstrate quite the same type of behavior, while the smallest area of emergence of chimera state is observed in the area of in the case of scale-free network. We hypothesize that hierarchical structure of the scale-free network suppresses the wide area of the chimera behavior. So it could be either spiking or silent in the wider area of parameters. Next, we demonstrate which pattern is associated with the chimera-like behavior in the Hodgkin-Huxley network. Here we ordered the network elements in accordance with the interspike interval, which is the analog of frequency in the spiking neurons. So we can see that for each network topology, we can excite such chimera-like behavior, which consists in coexistence of cluster of spiking elements and the cluster of silent network elements, which emerge under their interaction. Also, we were interested in how the process of excitation of these elements emerges in such networks. We compared 3 different types of topology, as I said before: scale-free, figure A, small world, figure B, and random network, figure C, and considered how the network elements are excited at different values of a current bias. So with increasing current bias, we see that network elements with the lowest degree, it means that these nodes are peripheral and coupled with the smallest number of the elements, are excited first. On the contrary, the hub elements, which have much higher degree, are excited the last. We can conclude based on this observation that network elements with a higher degree are more robust to the external influences of the current bias and remain silent due to the interaction with the other network nodes, which can switch them from the limit cycle to the fixed point due to the greater strength of external influence. Finally, our latest work, which was done with our colleagues from India, was done in the consideration of such interesting phenomena of chimera state intersected with the explosive synchronization in the ensemble of heterogeneous elements. It's obvious that previously we have considered the networks of identical elements, but in the real ensembles, real networks, such behavior, such choosing of network nodes is improper because one can hardly find the same identical elements in the nature. So they are more or less heterogeneous. So observation of such phenomena in a heterogeneous ensemble is vital for the development of this topic. So we have considered the Chromomoto equation, which is given in this slide, where the coupling term is multiplied by the local order parameter, which characterizes the coherence of the local population around the I node. And this multiplication gives the road to the explosive synchronization or first order transition, which is also given in the slide, like the illustration of this phenomena. The global network behavior is characterized by the global order parameter averaged over the time after the transient process, and the model parameters are also given in the slide. First, we considered the effect of frequency heterogeneity. We have distributed the eigenfrequencies of Chromomoto oscillators within the range from omega 0 plus delta and omega 0 minus delta, and we have chosen the uniform distribution of the eigenfrequencies. What we achieved is presented in this slide. First, let's take a look at the two-parameter plane, which represent the network dynamics on the plane delta versus lambda, where lambda is the coupling strength between the elements. Here, black area is incoherent network behavior. Yellow area is coherent. White dashed line represents the explosive transition, and the black dashed line represents the transition to coherence. In the case of completely homogeneous ensemble at delta equals to 0, we can see that the transition emerges quite fast from incoherent to coherent behavior, and both of the transitions, explosive and transitions to coherence, are happen in the same point. Increasing the heterogeneity of the ensemble, we achieve that the plateau of the order parameter, which is represented in the first figure A, for 3 different values of heterogeneity, which says that the transition from incoherence to coherence doesn't happen abruptly. So there is some intermediate state of partial synchronization which emerges after the explosive transition, and the range of this area linearly increases with the increase of the heterogeneity. So we wanted to take a more detailed look on this transition. We have fixed the heterogeneity equal to 1, delta equals to 1, and considered that the frequency distribution, the effective frequency distribution of the network nodes after the explosive transition, the dynamics of the network changes rapidly. So we can see one huge cluster with the pronounced same frequencies of the oscillators, and the small cluster where the frequencies are distributed and the elements are not coherent. After this area, we can see the coherent pi state where the phases are not equal, but the frequencies are equal, and this is the road to the complete coherence in terms of phase. Taking the look at the points A and B, we considered the profiles of the network behavior, and we obtain quite interesting phenomena, which results in the frequency modulated chimera-like behavior in the heterogeneous ensemble. What does it mean? It means that a large part of the elements is completely synchronized in terms of frequency, which is given by the top panel. And there is a small cluster of spatially localized elements with the frequency distributed in some range, and they are incoherent. Also, which is interesting, is that this cluster is not stationary in time. It demonstrates some dynamics, particularly its breathing, and at the smaller coupling strengths 0.048, it represents some intermittent behavior with irregular distance between the spikes, and at 0.051, we can see that the dynamics of this incoherent ensemble, incoherent part of the ensemble, is quite regular. So what are the mechanisms that leading to such frequency modulated chimera-like behavior? Considering the dynamics of the network versus the coupling strengths, we can see that increasing of the coupling strengths leads to the splitting of the ensemble into populations which are attractively coupled with the positive coupling strengths, and the repulsively coupled population, which is characterized by the negative coupling strengths. Interestingly, that and obviously that attractively coupled population is synchronized much faster because it has much higher conversions to the synchronized behavior. So its route to synchronization is much faster. On the contrary, a repulsive coupling is trying to suppress the synchronization. So the repulsively coupled elements form such a frequency modulated cluster, which is suppressed under the high coupling strengths. Previously, we have considered the effects of frequency modulated chimera behavior in the case of non-locally regularly coupled network. Now we will explore the influence of network topology and consider how the network behavior changes with increasing of the number of the local neighbors of each element. So the network topology remains regular and non-local, but we increase the number of the elements which are coupled with the current element. So the green curve here shows the previously considered situation. The red curve demonstrates the decreasing of the number of the elements. So we can see that the transition to synchrony occurs at the much higher values of coupling strengths. The region of chimera behavior is much wider here. And also we can see that going towards the global coupling, increasing the number of the elements, we can see that this phenomena, this effect of chimera-like behavior, vanishes under the global coupling. Interestingly, that at extremely low values of neighbors of non-local coupling, the bistability also takes place. During the forward transition, which means the increasing of the coupling strengths, the network behavior exhibits not the coherent state, but the traveling wave state, which means that the phase drifts both in space and time. However, while we go in the opposite direction, if we start with a high value of coupling and we decrease this value, we set to the stable coherent solution of the network behavior and go backwards on the red curve. So we are setting on the pi state, which is a road to the global network coherence. This bistability, this development of the traveling wave state, which is impossible at higher values of nearest neighbors coupling, emerges to the local, very much local character of interactions. So it supports the drift of phase and the heterogeneity of phase between the local populations, and during this interaction between the locally coupled populations, such drift of phase may appear. Finally, we considered the effect of small worldness on the considered effect of chimera-like behavior in heterogeneous network. Similarly to the increasing of the network, the number of neighbors in the network, we see that this range of possible area of chimera-like behavior becomes more narrow with the increasing of small worldness. It means that emergence of large-scale coupling have the same effect on the suppression of this chimera-like behavior as an increasing of the number of the elements. So at the completely random network at p equals to unity, we also see the sharp transition, first order explosive transition from incoherence to coherence without any intermediate states. And we conclude that emergence of such large-scale couplings between the network elements, not like just interaction within the local communities, leads to the influence of the network on the larger number of elements, and this influence supports this suppression. I think that my presentation is over now. I thank for everyone for the attention, and now I'm ready to answer the questions if one have. Thank you so much.
Thank you, sir. Thank you, Dr. Pralab, for your wonderful talk with splendid presentation. If any question from audience for speaker, can ask him.
Hello.
If no question, then let us thank him again for his nice speech.
I think that someone has the question.
Yeah.
Pulanda, one question at the chat box.
Yeah. Okay.
Please see.
No, I can't find any question in chat box.
Hello. Do you hear me?
Yeah. You can ask.
Hello.
Yes, Dibakar, we hear you very well.
Just 1 minute. Yeah. Do you hear me?
Yeah.
Yes.
Yeah. Just joint work. You have said that they just forward step, you got TW state, traveling wave state, and for backward you got just pi state. Yeah, this is the initial condition. Yeah.
I think that they didn't hear the last part of the question about the backward transition.
Yeah. Just due to different initial condition, you got pi state and TW state.
Mm-hmm.
No, this part. Yeah. This state, this slide. Yeah, but for pi state, you have taken just different initial condition.
The initial conditions are random, but the network converges to the pi state due to the very high coupling strengths. So this solution, the pi state solution, is much more stable than traveling wave state. So to settle on the traveling wave solution, we have to choose very explicitly the drifting initial phase distribution. But if we set the random phase distribution, this network will settle on the pi state, which is globally much more stable with respect to the traveling wave solution. However, we didn't observe the traveling wave in the other cases. So just in the case of small number of non-local neighbors.
Okay, fine, thanks.
Thank you for the
Thank
question.
you, sir. Okay, let us thank again him for his nice speech.
Holanda,
Yeah.
one question from Kalpojit Datta. Liouville theorem tells us that in phase volume, the volume remains constant. That is, the change in density of the particle remains constant with time. That is, entropy is constant. And the system involves. But when it applied to isolated system, it also gives rise to chaotic field, which violates the second law of thermodynamics. I don't find any question here.
I'm not sure that I get the question.
Yes, here are some information, but no question.
So let me thank once again the organizers for the possibility to give a talk on this webinar. It was an interesting experience, and thank you for the attention. Thank you so much.
Thank you, sir.
Am I audible?
Yes, yes.
Hello.
Yes. Yes,
Now
yes.
I am okay. Now I am inviting our last honorable reputed speaker in this session, Dr. Dibakar Ghosh, Associate Professor, ISI Kolkata, to deliver his valuable lecture. And in this session, on behalf of webinar organizing committee, I would like to request Dr. Sanut Kumar Mahato, Sidhu Kanu Birsa University, India, for chair this session. Dear participant, please enjoy this session with our speaker. Now I handed over the session to our chairperson.
Thank you, Dr. Amanatullah. for giving me the opportunity to chair the session. I welcome Dr. Dibakor Ghosh from Department of Physics and Applied Mathematics Unit of ISI Kolkata. So this is a great time to have with us Dr. Dibakor Ghosh. So before starting the session, I would like to introduce Dr. Ghosh before you. So as per the information, Dr. Ghosh is renowned person over the world, and he has lots of publications, lots of works in the field of mathematics, nonlinear dynamics. Dr. Ghosh has done his BSc and MSc from Calcutta University and PhD on nonlinear dynamics from Jadavpur University. Dr. Ghosh has a long teaching experience. He started his teaching in the Dinabandhu Andrew College, Kolkata from 2006. Then he joined Kalyani University in 2012, and after that he joined to ISI Kolkata in 2012. Presently, Dr. Ghosh is the associate professor in mathematics at ISI Kolkata. Dr. Ghosh has huge age index, it is 29, and huge number of citations, more than 2,400 citations, and he has published more than 117 reputed research papers. Dr. Ghosh has already guided successfully to PhD scholars from his able supervisorship, and presently Dr. Ghosh is guiding 6 PhD scholars. Dr. Ghosh has also guided 3 postdoc scholars, and he has already supervised 2 projects, national and international. Dr. Ghosh has been working in the editorial board of several international reputed journals like Journal of Nonlinear Dynamics, Journal of Applied Mathematics. Dr. Ghosh has been awarded as the Distinguished Referee in Europhysics Letter twice in 2018 and 2019, and also he was awarded the top cited author in 2019. Dr. Ghosh has guided or supervised many research projects, national and international, and also he is carrying out the SCRB-DST project presently. So we feel proud that we have such a personality with us in this international webinar, and the topic of deliberation by Dr. Ghosh is extreme events in nonlinear dynamical systems. It's a very interesting topic. So I hope all of you us will be benefited from his lecture. So I request Dr. Ghosh to start his presentation now. Dr. Ghosh, can you listen me?
Yeah,
Okay, you can start now.
thank you for your nice introduction. And yeah, my voice is clear,
Yes, continue.
and my skin.
Okay, fine. Just make it full screen.
Yeah, just I'm doing.
Okay.
Yeah,
Fine.
it is clear,
Fine. Fine. Continue.
but I can't see you. That's the problem. It's okay.
Okay. Continue.
Thanks the organizer for inviting, and especially thanks to my students Pintu to organize this seminar in these difficult situations. Today in my talk, just I will discuss a very hot topic and very interesting topic nowadays, extreme events in nonlinear dynamical system. The plan of my discussion is just not to show you the details result of my or others people. Just I will give some basic idea on extreme events and how to study, why you study extreme events in nonlinear system, nonlinear dynamic systems, and the mechanism of extreme events in dynamical systems. For mechanism up to now, there are 3 or 4 types of mechanism are investigated because the field is very emerging field, and just last few years this research has been begin, and we are working on this field and some people are working on this extreme events. Before start my talk, just I introduce my collaborators who are involved in these extreme events. Not all collaborators. My collaborator Gopal Krishna Bosak, my colleague ISI, Stat Math Unit, and my long collaborators Samal Kumar Dana and Thomas Kapitaniak, and my friend Chitranjan Hens, he is an Inspire faculty at ISI, and my students Annobre, who is working on extreme events for his thesis, and Sainton Nag Chaudhary, and Sarvind Rokhit, Somen Maji, and Oindo Mishro. Oindo Mishro is a PhD student of Samal Kumar Dana. He is working with me. Before show the results or mathematical formulation on extreme events or how to study extreme events, just I will show some natural events which we call extreme events. The first one is cyclone. We already know just few months, 2 months ago, just we faced this problem near Kolkata, and the flood in 2018, Kerala flood, and tsunami 2004, and log waves. All these events we call as an extreme events. Why we call extreme events, I will discuss later. And another example, Calvan boom and dot and earthquake, very recent earthquake in Turkey, January 2020. And also, this type of events also occur in epidemic spreading the COVID-19. There is no interaction for COVID-19. Epileptic seizure. My collaborator Nikita is working on epileptic seizure from EEG data of human brain and shows some extreme event-like behavior. Also, this event also occur in powered blackout system and also share market crash. So, extreme event is occur for natural events as well as for some man-made systems. So, the first question is, why we study extreme events in dynamic systems? What is the necessity of this study? Because we can't control the extreme events which are occurring in nature. But we can, if we study extreme events by mathematical point of view, by constructing our mathematical modeling, then we can at least we can understand the dynamical origin of the events, and we can control or we can predict some extreme events in our man-made system, so that we can so that damage on human life will be less. From the above experimental data, measurement data, just 3 properties were noticed. The events are very rare. Very rare means the occurrence of probability of the event is very less. And the events are large deviate from the nominal state. The distribution of these events are in non-Gaussian type. So I show this a schematic diagram of some data from 1990 to 1980. Just here we show that the red curve, we call this a threshold. I'll discuss just 2-3 slides later what is meant by this threshold, XT event threshold. Just you see that just some of the events are crossed this threshold. Only 5 events are crossing this threshold. The events which crosses this threshold we call as XT
Hello,
events.
hello,
Yeah,
hello.
Subhas. Hello. You any problem?
Okay, sir, continue.
Do you hear me?
Khajanchi wants to tell something. Dr. Khajanchi. No. Dr. Ghosh, continue.
Yeah. Yeah, do you hear me or?
Okay, okay, continue. Your slides are not showing right now.
Oh, slide I just off. Yeah,
Okay.
it's okay.
Okay, fine.
Yeah, if you press problem, just call me, just inform.
Okay.
Just 1 minute. Yeah.
Okay,
So for the study of XT events, the prediction is very important. Just we are concerning about what's the next earthquake will be happen, or what the next cyclone like Amphan will comes. In this time, the prediction on timing and prediction on the intensity of the events both are important. So from this study, we just interested on mainly on dynamical origin of the XT events, their predictions, and also some control scheme on dynamical systems. From real data, the big problem is the availability of events or availability of data is very small. So from if we use the dynamical system concept, then we can create large number of events and we can create large number of data. From real data, the probability distribution is also difficult because we have only few data. So we suggested a study of dynamical systems to obtain large number of events that help produce an effective estimate of average return time of the events. So what is meant by XT events in dynamical sense? This large data and large amplitude appear for relatively shorter period of time compared to regular behavior of the system. That is, in the left figure, you can see the blue curve starting from here. It will most of the time it will stay on this plane. But when it comes to this RC region, that is RE region means the region of instability, it will come very close to this. Then the trajectory will go away from this plane, and after a short time, it will come back again to the plane. So this large deviation from the amplitude or a very relatively shorter time of period to the regular behavior of the system. But these events are recurrent and seem to occur in several natural and man-made systems. The statistical distribution of occurrence of such occasional large amplitude spiking events show qualitative similarity in dynamical sense with the data recorded of natural events like rock waves, earthquake, tsunami, flood, and share market crashes. So in dynamical system, the trajectory of dynamical systems may fluctuate around the central tendency for most of the time. However, it can occasionally live far away from that nominal value. We can observe a state variable of the systems, or we can define an observable Qt equal to some function of the observable function of the state variable to reflect the sudden and rare large deviation of the trajectory for a long time series of the events. So in dynamic systems, an event we call as an extreme event if the events are short-lasting events and they are recurrent, aperiodic, and defined amplitude having amplitude greater than a predefined threshold. I will discuss what is meant by predefined threshold. These events occur much more often than Gaussian distribution. And their occurrence of probability is very small. One thing I just tell you, the extreme events are rare events, but the rare events are not extreme events. Just if the rare events crosses some threshold, then we call this an extreme events. So before the study of extreme and dynamic systems, we have to first distinguish the extremes from the regular events. There are some methods like block maxima method, peak over threshold method, mean axis function approach, and other percentile approach. There are 3 or 4 approaches are already available, but the most commonly used methods are block maxima method and peak over threshold method. In this block maxima method, this is a technique to estimate maximum or minimum of each block from a long time series. In this schematic diagram, just you have noticed that this is schematic diagram, just time 0 to 100. Just we divide each block into 10 blocks and with length 10. And we collect the maximum point in each block. So basically for a long time series, we divide the long time series into b number of blocks of length k, such that n equal to bk. This method gives b number of potential extremes from the whole time series. It is widely used to investigate the extremes in financial and climatological data series where the maximum in each block is important. To construct a statistical model of using this block maxima approach, for climatology model, the maximum temperature in a year is a natural and common choice of bin length. And the corresponding, if we first collect these extremes, then we want to fit these extremes using some statistical model. The generalized extreme value distribution, that is, if we collect the extremes from this block maxima method, the statistics of these extremes converts to generalized extreme value distribution. The generalized extreme distribution is a 3 types of distribution combining Gumbel, Fitchett, and Weibull in the this form. Just here xi is the shape parameter. This is also called the tail index. After normalizing or standardizing the real location parameter and also their scale parameter, gx or gy belong to one of the 3 non-degenerate distribution families. If the tail index, that is xi, equal to 0, then it shows exponential tail, that is Gumbel tail. Just in this figure, just if you see the green curve, very light curve, and for xi greater than 0, it will shows heavy tail, that is featured type, and xi less than 0, that is upper bounded tail or Weibull type. In dynamical system, due to bounded phase space, most of the time the distribution will be upper bounded tail. So most of the time the distribution is of Weibull type. But the problem is for block maxima method, many of the excellent candidate near to extreme events are neglected due to the choice of maximum point in each block. So there is a disadvantage of this method, using this method, block maxima method. For one-to-one correspondence between block maxima and the statistical model, one should consider large number of data. In some real data, this is not possible always because we do not have large number of data, or in the limit of very large k in each block. The basic problem with the block maxima approach is that many excellent extremes are neglected due to considering only one extreme or one maximum in each block. An important property of clustering event is extreme event is clustering, which is usually occur in earthquake. What is meant by clustering? Clustering is sequence of extreme events, sequence of events within a short interval of time. These correlated and clustering of events are not identifiable using this block maxima method. So we can overcome this by using this method, peak over threshold method, where an event is treated as extreme if it crosses a predefined threshold t equal to m plus d sigma, where m is called mean of the whole data and sigma is standard deviation and d is some multiple by multiple, it will be integer, positive or negative integer. Just in this schematic diagram, just I draw T1, we first draw T1 for suppose d equal to 2 or T2 d equal to 4, T3 d equal to 5. Then you will see that the events which is above this threshold T1, T2, T3 will consider as an extreme events. The statistics of peak over threshold method converge to two-parameter generalized Pareto distribution. The form is this. The above two distribution, that is generalized extreme value and generalized Pareto distributions based on block maxima method and peak over threshold methods, are equivalent in the asymptotic limit if the suitable conditions of time scale correlation are met. For a long data set, the derived information is equivalent, although the extraction process for extremes are different. If one has to deal with finite data or define extreme events by taking block length, k should be very large or moderate k should be chosen. The choice of k and choice of bin or blocks is very important for the study of extreme distribution function. So we have to care on this. And for the limiting case, these two distributions are related by this formula. Here I just give some step. What is the process to study extreme events in dynamical systems? First, we have to observe the sudden and intermittent large expansion of the dynamical systems by changing the parameter. You have to first notice this sudden and intermittent large expansion of the attractor. Then you have to define an observable or we have to select some state variables which gives the exact figure, exact physical meaning of the whole system. Then extract, the third step is extract the extremes from the regular events using either block maxima or peak upper threshold or any other methods. You have to extract the extremes. In block maxima method, divide the time series into b number of bins into k data, and then you have to fit the compatible with the generalized extreme value distribution. Then we have to conclude that the block maxima method, if it is fit, then you can conclude that the method is okay. Otherwise, you have to change it to collect the peaks from peak upper threshold method. After matching with the some distribution function, you have to change the system parameters and locate the parameter space where why these extreme events are occurring. That is, there is some instability region in the phase space. We have to collect, you have to identify that parameter space. Then the natural question is, can we predict this event? This is a very challenging problem and very difficult problem in our real life problem. So we can predict, we can try to predict using some statistical method or recently developed machine learning approach. We can predict the return time of the extreme events. The next question is, we are studying a dynamical system. The dynamical systems are deterministic dynamical systems. But we are using the statistical modeling and extreme value statistics. Can we link between these extreme value statistics and the theory of dynamical systems? Or what is the importance of the study of extreme events in dynamical systems? The linking between extreme value statistics and theory of dynamical systems is possible by the observation that dynamical systems generate infinitely many random processes. The extreme value statistics originally developed to find the distribution of the maximum or minimum set of n independent and identically distributed random variables. That is, initially the extreme value statistics was developed for IID random variable. Later, this theory is extended for random variables which are weakly correlated. The time series or the observable of dynamical systems are correlated, but the extremes are uncorrelated. So, the condition on the correlation of stochastic process for extreme value statistics is met. This gives a promising idea to link a mathematical framework suitable for extremes and the dynamics in a physical systems. Two widely used methods to find extremes from the time series are block maxima and peak upper threshold method. Next question is, what is the importance of study of extreme events in dynamic systems? Because extreme events, each extreme events are devastating effect on human life and economy. Just we can notice few days ago the cyclone Amphan. So extreme event has become an important topic of current research. Prediction or early warning of extreme event is most important to mitigate a disaster. Since the prediction of extreme event is the most difficult task, specifically from time series, so a recent trend has started to understand the origin of extreme events from simple dynamical model studies or using some experiment like laser, optical device, EEG data of human brain, electronic circuit, etc. Some successes were made at least to create extreme events in both model and experimental data and to understand the nature of their evolution. Usually when an event deviates from a nominal value by a few standard deviation, then it is declared as an extreme event. However, there is no clear definition, especially in the context of natural events, since a relatively smaller events can also make a huge damage. Just you can think that the heavy rain in summer can make a flood, but in winter, in rainy season, a medium rain can make a flood. So next we just discuss some of our few results. The basic concept is we can find the mechanism. What is the mechanism of extreme events? For this we just first study an Ikeda map, then on moving agents, then heterogeneous network of Josephson junction, and then recently we have studied El Nino Southern Oscillator. One type of mechanism in interior crisis. There are up to 4 or 5 mechanisms are investigated till now. Just we have investigated just Ikeda map, just very simple map, two-dimensional map. The map comes from laser model, and we just fix all the parameters. For dynamical system study, if we have more parameters, we have to fix most of the parameters and vary 1 or 2 parameters which are important. So we choose here P as a bifurcation parameter. So in this bifurcation diagram, the left hand side, this say P equal to 7.25 to 7.27 in this region, these regions are bounded chaos. So there is no extreme events. Most of the times, all the times the trajectory stay in the bounded space. But when the parameter crosses this threshold, it comes to into a crisis where sudden expansion of the attractor occurs, and this system shows extreme event like behavior. If we increase the value of P, then we see that the events are very often. That is, we can say these are extreme events. The red line, we have to threshold using peak over threshold, mean minus 5 times standard deviation. Just we see that P equal to 7.2 value we have taken here. Just this is a time series where red line are the threshold using peak over threshold. The data below this red line we consider as an extreme events. We collect this data and the height of this data, and if we see the distribution, we can see that the distribution is bounded tail, and that is Weibull type of distribution. And if we see that inter-event interval IEI, then it looks like Poisson-like distribution. But if we increase the parameter value, just after the post into a crisis, then the last number of data comes and the number spike increases. And the corresponding distribution also shows the inter-event interval also shows Poisson-like distribution. The next one, just we have taken El Nino Southern Oscillator, and we observe that the merging of pure adding and pure doubling bifurcation is the instability region, and for the reason for these extreme events. Just see one just bifurcation diagram from left hand side, that if we increase the epsilon value, it will at first it will give pure doubling root to chaos. Then it will show some bounded chaos, that is a lower panel left side figure, bounded chaos. After it is sudden jump of the attractor, and if we see the epsilon equal to 0.18, and if we decrease the value, then we show that pure adding cascade, that is number of small period is adding 1 by 1. 1 to the power 0 means only one upper orbit and one orbit upper, one lower. In this way, 1 to the power 1, 1 to the power 2, just one period is adding with low amplitude. When this period adding and period merge, doubling are merged, then the XT events are occur. Then we consider just whether this XT events is emerged in a network of globally coupled network. Of course, we have taken a Josephson junction with heterogeneous parameter. Just phi I dot equal to yi and yi dot equal to something, and here k is the coupling strength and y is the mean field coupling, and we consider k as a repulsive type, that is negative, and we introduce alpha I, the damping parameter. We introduce heterogeneity through this parameter alpha I. Then we see that the whole population divided into three groups. The first group is blue. It shows always rotational motion, and the red curve shows it is librational motion. And between these two regions, yellow regions, it will shows extreme events. So most of the time, the oscillator stay in the libration state, but occasionally it will comes to rotational state, and it will cover the whole phase. And this type of XT events we observed recently, and this is not parameter system dependent. It is also observed in Landau oscillators and other oscillators which we observe. Recently, you have observed XT events in mobile network. That is a network of random variable, network of time-varying network where the nodes are moving in some physical space. In this schematic diagram, just we have fixed some parameter space, physical space. If the node, if the agent randomly moving and come or fall into this region, then these three regions are interacting. And this color, pink color or something magenta color, this color shows that the events, those events come into this region, they are repulsive. That is we consider two types of coupling, attractive and repulsive, into the same time-varying network. Then this is a network, so large number of oscillator here. So our target is to study the synchronization, whether the system is synchronized or not. But if we see the parameter space, Ka means attractive coupling and Kr means repulsive coupling. For small value of Ka or Kr, the system is desynchronized. If we change, if we increase the parameter value of Kr, that is repulsive state, the system goes into extreme event state, and for higher value, it will intermediate state and then synchronized state. But in this state, extreme event region, the time series error, it will shows on-off intermediacy. That is the trajectory stay most of the time on the synchronous manifold, but occasionally it comes, it is go away from this manifold and come back again to the manifold after a very short time. If we see the distribution, corresponding distribution, we see that the HS means the threshold T here. And for this paper, we just calculated the threshold for variable distribution. It gives us T equal to M plus 8 sigma. That is HS equal to mean plus 8 times of sigma. And the events just right side of this threshold are XT event threshold, XT events. These portions are called tail of the distribution. So conclusion part is just to have discussed only the necessity of the study of XT events in dynamical systems, and there how to study XT events in deterministic systems, and also some statistical distribution functions. Mainly I have discussed two types of distribution functions, generalized XT event and generalized pattern distribution. And location of instability in dynamical sense, that is dynamical origin of XT events, and there are some three mechanisms. Thank you.
Thank you, Dr. Dibakar. Now I may ask for some questions from the participants.
Yeah,
So
of course.
please, participants, you can ask some questions. Anybody? Dr. Khajanchi? So I think there is no question from the participants. Anybody? So thanks a lot, Dr. Ghosh, for your informative and nice presentation describing the different prediction models of dynamical systems. So it is very much important to study the dynamical system in the present era of in the case of climatic change or any natural phenomena or everything livelihood phenomena can be described in terms of dynamical systems, and Dr. Ghosh has nicely presented many of the mechanisms, many of the methods to describe the prediction of different phenomena, different dynamical systems. So this is a nice presentation, and I hope we shall go forward through his presentation and lectures. So thank you once again, Dr. Ghosh. I am proud to say that Dr. Ghosh and myself are of the same batch. As per
Yeah.
CV, I can see that I also passed a BSc in 2002, and he also, and we have also joined in the teaching in 2006, both of us. So this is a great
Yeah.
pleasing moment that we are in the same platform. So I hope we will
Yeah,
interact.
very nice.
We shall interact more later on. So thank you. Now can I request Dr. Amanatullah to continue?
Thank you, our honorable speaker, Dr. Ghosh, for his wonderful and informative talk. And a special thanks to our honorable chairperson, Dr. Mahato, for his for giving us his valuable time from his busy schedule. And also thanks to our participant for their cooperation. Now we arrive at the end of second day's program. So I declare that today's program is stopped and stop here, and we will join again tomorrow at 10:45 a.m. So thank
Dr.
you.
Amanatullah, somebody want to ask some
Yes.
question to Dr. Ghosh. Kalpajit Datto. Kalpajit Datto,
Yeah. Yeah, please ask.
please ask the question.
No, yeah, he already written. The question is for Haidar sir.
Oh. Kalpajit
Sorry,
Datto. What is the question? I can't find the question.
yeah, so thank you again
Okay,
to all of
okay.
you.
Kalpajit has given. Whether we live in a random or deterministic universe, we cannot accurately predict something seemingly trivial as the weather. We can barely predict the weather conditions within 7 days or so. Why is that?
Because in weather systems we also predict. For the case of Amphan, you just notice that after before 7 days we are very aware that this day and this time the Amphan will come. But we have sufficient data on climatic weather season, but the prediction is not long term prediction. It was a short term prediction.
Can
Can you tell me more
tell you
turbulence
more
and
about
gravitational theory?
turbulence and the Navier
No, no,
string?
I am not working on this field.
Yeah. This is a different thing. That
Yeah.
goes to the fluid mechanics and fluid flows boundary layer theory. That's all. So, any more question? I think Dr. Ghosh has explained nicely. So I again request Dr. Amanatullah to continue this session.
Thank you again to all, and we stopped this session here. Thank you.
Thank you, everyone. Thank you.